Welcome to Easy Elim Learning Simplified. My name is Ruth, and today we are going to be looking at the topic the mole. And our subtopic for today is titration. So we're just going to introduce a little bit on what titration is. We're going also to mention the different types of titrations, and then in a later video we are going to dive deep into those types of titrations. So first of all, titration is an experimental technique used to determine the concentration of a known solution. So it usually involves mostly you notice you'll be working with acids and bases. This can be soluble or insoluble bases. So that is what we are going to be using for this for titration experiment. But it can also be extended to any addition of one solution to the other to find out the amounts required for reactions. So since volume measurements play a key role in titration, it is also known as volumetric analysis. And a reagent called titrant or titrator is prepared as a standard solution. So a known concentration and volume of a titrant reacts with a solution of an analyte or titrant whose concentration is unknown in order to determine the concentration. So you notice for the titrant, you'll be placing it in the conical flask, and then the one that is being analyzed will be placed in the burette. And then we're also going to be using indicators to help us get the endpoints. So the procedure usually involves adding one solution to the other in the presence of an indicator, which shows that the solution has completely reacted. So, and then if the concentration and the volume of one of the solution is known and the volume of the other solution is known, then the unknown concentration can be calculated, provided the stoichiometry of the reaction is known. Stoichiometry, we already discussed it, is when that reaction has occurred, you've written correct equations that can get the mole ratios. So you'll notice that in the calculations of titration, we are going to be applying a lot of the things that we have been discussing. We are going to calculate the conversion between mass mole and molar mass, and then also we are going to introduce concentration method and then use stoichiometry to do calculations. So when we get there, you'll notice that so during volumetric analysis, the solution whose exact concentration is usually known as the standard solution, as you have said, and then the one that we doesn't have the concentration which we are trying to look for is known as the analyte. So in the steps of titration, we usually fill the burette with the acid. The burette is used to place the acid of an unknown concentration. And then the alkali is added on the conical flasks using a pipette. So you can use a pipette filler or you can use the mouth to fill the pipette. And the pipette also gives an accurate volume measurement. And then an indicator is added to the alkali. The indicator is added to the alkali in the conical flask, which causes a color change to occur. So when titrating a strong acid with a strong acid alkali, so you need to note this. When it's both of them are strong, you can use any commercial indicator. But if you are titrating a strong acid with a weak base, you're supposed to use methyl orange. And if you are titrating a weak acid with a strong base, you use phenolphthalein. You'll notice you'll be using phenolphthalein quite often. It's because of the color changes of phenolphthalein. It's usually easier to use phenolphthalein. So the acid is added into the alkali. The acid from the burette is allowed to run into the alkali, swirling constantly to ensure the reactants mix well. And then when the color starts to change, we add slowly, drop by drop, and then stop when there's a permanent color change. And then we record the value that we get, which we call the titer, in a table. So this is how a table usually looks like. This is just a sample of the titration table. You notice we usually have 3 titers. We do the experiment 3 times. We have the final burette readings on the burette, the initial readings and the difference. It doesn't have to necessarily mean that you have to start at 0 degrees. You can use 0 centimeters cubed, that is, but you can start from where you left off depending on the values you got from the first titration. So like for example, in this case, you notice that the burette reading was filled, and the burette reading is usually has a maximum of 50 centimeters cubed of solution. So when we ran and added the acid into the base, we got, when we read the burette, we got 20 centimeters cubed. When we are filling the table, we can fill it into 1 decimal place or 2 decimal places. It needs to be uniform across. So when we are marking the marks for the table, the table must be completely full. There's a mark for filling the table, but not just filling the table, the decimals should be consistent. Consistency means if you decide to use one decimal place, it's one decimal place throughout. If you use two decimal places, it's two decimal places throughout. But for the second, decimal places can be 0.0 or 0.5. It can't be any other value. So that's how the table is usually filled. So when we are calculating the concentration of a titrant, the known volume and the concentration of the alkali enables the moles to be calculated. So remember, molarity is, or concentration, is equals to moles over volume. So if you have a volume and concentration, you can be able to calculate the moles comfortably using the formula or the first principle method. So a balanced symbol equation enables the mole ratio of the acid and alkali to be determined, and the number of moles of acid can be calculated. So the mean titer is the volume of the acid, and then using moles and volume, the concentration of the unknown acid can be determined. So the first question you always see in calculations on titration is calculating the average volume of solution used. Basically, this is the average volume of the solution in the burette. So you always take the 3 titrations. In our case, we had 20.0 centimeters cubed, and you divide by 3. Do not separate, do not do this. If you do this, you're not going to get that mark, especially when we consider KCSE rules. And then 20 plus 20 plus 20 gives us 60.0, then you divide by 3. You're not going to get it because you didn't introduce the 3 from the beginning. So make sure you get also the correct decimal places and also the units so that you can get the full marks. So the average volume is usually 1 mark. The 1 mark is for the accuracy and also the calculation itself. So when it comes to the rules for marking of the table, we are going to go that into details later when you look at paper 3. But it is important that your table should be completely filled with the 3 titrations. And then when we are averaging, also we have some rules for averaging, which we are going to discuss later on. So when you are doing calculations, especially for moles, we shall leave our moles to the 4th decimal places. It helps us to reduce the error that is in the process. So let's do 1 or 2 questions in regards to titration. We haven't yet gone to specificity of the specific types of titration yet. This is just to help us to know using titration we can be able to get concentration of a known solution. So for example, in this question, it says titration reveals that 11.6 ml of 3.0 sulfuric acid are required to neutralize the solution of sodium hydroxide in 25 ml of sodium hydroxide solution. What is the molarity? So when you look at sulfuric acid, what do we know? We have the volume, which is 11.6 ml or centimeters cubed, and we have the concentration, which is 3.0 m. And then for sodium hydroxide, we have volume, which is 25 ml or centimeters cubed. From the sulfuric acid, also we can get the molar mass. So molar mass for sulfuric acid will be 1 times 2 plus 32 plus 16 times 4, which will give us 98. And then for sodium hydroxide, the molar mass is 23 plus 12 plus 1, which gives us 40. So those are the information we have. So the question is, you have been asked for the molarity of sodium hydroxide. We know that molarity is equals to number of moles in our volume in a liter. So when you look at this equation, this formula, we have the molarity already. We can get, with the question is on volume, so we need the moles to be able to get the volume. So how can we get the moles? We can get the moles from the stoichiometry from sulfuric acid. So we said stoichiometry, you have to write the equation first. So it is sulfuric acid plus sodium hydroxide to give us sodium sulfate plus water. So we balance this equation by putting a 2 here. and then we also put a 2 here. So the mole ratio is going to be 1 is to 2 is to 1 is to 2. So the next thing, using the mole ratio, we get the moles of sulfuric acid so that we can use the mole ratio to get the moles of sodium hydroxide, which we want. So what has we been given from sulfuric acid to help us to calculate? So we have volume and molarity, so we can use that. We do not have to use the molar mass. So for sulfuric acid, it's 3m, which tells us is 3 moles in 1,000 centimeters cubed. So what I'm using right now is the first principle method. You can use the formula. So 3 moles are in 1,000 centimeters cubed. What about in 11.6 centimeters cubed? Remember, ml is the same as centimeters cubed. So how many moles are those? So it is 3 times 11.6. You divide by 1,000, which gives us 0.0348 moles. And these are the moles of sulfuric acid. So if you look at the mole ratio of sulfuric acid to sodium hydroxide, you notice the mole ratio is 1 is to 2. So we already have the moles of sulfuric acid, which is 0.0348. So the moles of sodium hydroxide, if 1 is 0.0348, 2 will be 0.0348 times 2, which will give us 0.0696 moles. Now we have fulfilled what we wanted. Now we have molarity of sodium hydroxide. Remember, these are moles of sodium hydroxide. We have molarity of sodium hydroxide. We have moles of sodium hydroxide. So getting the volume is easy. So you can input these values in the formula, or you can use first principle. So when you look at molarity of sodium hydroxide, is what we are looking for. So we have the volume, which is 25, and the moles now, not the other way around, and we are looking for molarity. So if 0.0696 moles are in 25 centimeters cubed or ml, what about in 1,000? So you can go ahead and input the moles and volumes, and remember to convert your volumes in liter before you use the formula, and you will still get the same answer. So using the first principle as we finish up, a 0.0696 moles are in 25. What about in 1,000 centimeters cubed? So it is 0.0696 times 1,000, you divide by 25, which gives us 2.784 m, which is the same as 2.8 m. So that's the molarity of sodium hydroxide. You've seen how we have incorporated the concentration stoichiometry in this calculation. So that's basically what we were talking about when we talk about titration. So you use um, the known solution, or the values of the known solution. In this case, our known solution was the sulfuric acid. So we took the moles, we calculated the moles of the known solution, which is sulfuric acid, which we got as 0.0348. And then when we write an equation, you get the mole ratio of sulfuric acid to sodium hydroxide. And then using now the moles you've gotten, you can get the moles of the unknown, which was sodium hydroxide. Now we end up having moles of sodium hydroxide, and we have the volume, so we can get the molarity comfortably. So that's how titration works. The purpose of the titration is to get the volume or moles or concentration of the unknown solution. So later on now, when we go to the specific types of titrations, you'll see how the calculations differ. But at the end of the day, we are ending up looking for the concentration of the unknown solution. So there are generally two types of titrations. We have direct titration, where the titrant is added to the analyte until a reaction goes to completion. And then we have the back titration, where the excess reagent is added to the analyte, and then the excess is added to a reagent that is determined. And these two usually are the main that can be further subdivided into others. So we have the acid-base titrations, in which an acidic or a base titrant reacts with the analyte that can be a base or an acid. We have also complexometric titrations, which involve a metal-ligand complexation reactions. We have precipitation titration, in which the analyte and the titrant react to form a precipitate. And then we have redox titrations, where the titrant is an oxidizing or a reducing agent. So you notice in the Form 3 syllabus, you talk about the direct titration, back titration, and the redox titration. We're also going to involve standard solutions because we mentioned them before and how they are usually used in regards to titration. So those are the ones that we are going to look at. The other ones, you're going to look at them later on in campus. So that's it for today. So in the next lesson, we are going to be looking at direct titration. So see you there.